Welcome back, everybody. Okay, looks like we lost a couple. No, I hope everybody's back. Luminita Jackson, are you here today? I don't see you.
Yes, I am.
Yes, you are. Fantastic.
Thank you. I appreciate
All
it.
righty, then I don't. All right. Okay, first question. Everybody familiar with where on Canvas they can go get their uh, chapter textbook, all their textbook, I should say, where to get all the information? No surprises, right? I hope everybody's gotten in there and played around with Canvas and looked around and see where everything's at, where you can find your homework, where the exams will be, so on and so forth. Okay. All right. Also familiar if you need tutoring, where to go to get tutoring. I also mentioned that on Tuesdays and Thursdays, I do have time in between my classes. Not every Tuesday and Thursday, but if you need time with me to ask questions, feel free to shoot me an email, which by the way, again, I repeat, email through Canvas, please. If you use my EDU, I get all kinds of other email every day, and I don't want to lose your email. Okay, so Canvas, I get nothing but you guys. That's it, nobody else. All right, so let me see what else. Any questions so far? All right. Well, I tell you what. Yeah, go ahead.
Sorry,
No
I
problem.
couldn't get the button to click. But I was just wondering, just to make sure, when we do our assignments and stuff, we can click away in the middle of that, right? Like we don't have to do it all at once. Okay.
Yeah, exactly. For assignments, other than exams, you know, like I said, you can use whatever resources you want for the activities, the assignments, homework, and so forth. It's only at the exams that we are actually the log is on and we can keep track of what's going on. Okay.
Okay. Thanks.
Yeah. And I know sometimes one might say I can, you know, I can click away. I can tell you this, given the time constraints that you have to do that exam, and if you were to click back and forth looking for the answers, you're going to run out of time. Okay. So, you know, just treat it as an exam as you would do if you're going face to face, and then you can come in and knock it out and you're good to go. Okay, good question. Any other questions? All right, well, let us jump on this. And we ended up on slide number 5, and now we're just talking about the areas of chemistry as if there is. Oh, let me make sure. Okay, recording's on. Just like any other professional field, there's a variety of different, you know, subgroups, if you will. Mine is organic chemistry, as I mentioned, synthesizing organic compounds. I kind of fell into that because I kind of being in construction for many years and working in that field. I like to build things, and when I got into chemistry, I started to build molecules. I just did the thought process, which to me was the same. Anyway, chemistry basically involved. I'm not saying it's the most important class you ever got to take. All I'm saying is this: it's all around you. Everything, literally everything you touch. Not to mention just sitting there listening to me, the chemical reactions that are occurring in your body. Everything that we can touch involves chemistry in some manner. Making the plastics. If you're running off a battery right now and your electronic device, there's a chemical reaction occurring in your batteries to generate electrons. And these electrons that are created are running your electronic device. These similar type of electrons that give you that crazy hair day if you wake up and you got this hair popping out, you know, or electrons that give you a shock when you touch something after walking on carpet. But those electrons are very powerful. We have a lot more to say about that. All right, as a science, we use what is called the scientific method. So you may want to be familiar with this particular method. There's a variety of different steps. Not complicated. In fact, you probably even do this yourself without really thinking about it. Okay. And so the first step in this is an observation. You may observe something happening, some phenomena going on, and you make an observation. For example, you put a soda bottle and you stick it in the freezer and you come back a few hours later and that thing just exploded all in your freezer. So my soda exploded in the freezer. That's your observation, for example. And so you formulate a hypothesis on that, on the observation. Your hypothesis is simply another way of saying it is, what do you think happened? What's your best guess given, given the information that you have on hand? So you formulate a hypothesis and you come up, for example, and say, maybe ice expands when it freezes. Okay. So then scientists, after we come up with a hypothesis, we go and look up in the scientific papers and see if anyone else has done that. We research the literature, find out, look to see if anyone else has done any type of work on this observation that you had. Well, they may not, but in either case, then you sit down and you perform experiments. You formulate some experiments to kind of maybe change the variables. It's all about variables. You might do things like, okay, let me try a bigger bottle. Okay, let me try different volumes of soda. Let me try different types of soda. Maybe that particular soda that had happened the first time was a fluke. So let me try the same one again, see what happens. So you design a variety of different experiments and repeat and see what happens. Okay. You analyze your hypothesis based on your results of all the experimentation you did. And if needed, perform more experiments to repeat the experiments and maybe formulate some more different types of experiments with different solutions, maybe orange juice versus soda pop, things of that nature. Excuse me. Draw a conclusion. You analyze your hypothesis, repeat the experiments as needed, and then finally you draw a conclusion. And you might say that, okay, based on the data that I have my conclusion is that one, ice expands when it freezes based on my data. My data supports my hypothesis. And you might take all your data and so forth and write it up and have it published in some literature. And hopefully other scientists would then look at it, read it, and repeat it, and hopefully it gets repeated. There has been publications that have been out there that people cannot repeat. I would say about 15, 20, actually in the 80s, there was a paper that came out that actually created. It kind of violated the laws of physics, and they were basically creating fusion. Fusion is the coming together of atoms compared to our like our sun. Hydrogen atoms are coming together and being fused together, as compared contrast to a fission where it blows up like the atomic bomb. Anyway, long story short, there was room temperature fusion going on. Oh, it was a hot topic for a while. It turns out it was just a fluke. They just didn't analyze their data. But anyway, that's our quote scientific method. So you may want to be familiar with the individual steps involved in the scientific method. Observations are important. You do in the lab. Observations. Keep track of things and what's happening. A lot of the stuff that I helped make when I was in the industry, it was actually stuff that normally I would have thrown away, down the trash or done, but it looked kind of interesting. And so we went in and looked at it again and, came up with some interesting things. Anyway, so things like color, clarity, the states of the matter. In other words, is it solid, liquid, and gas? We're going to be talking about these states of the matter. We will deal with these three of these states. There are four. Plasma is the fourth one, but we won't be talking about that. Plasma is like the northern lights, that is plasma, which is basically just charged particles up there, different, the fourth type of matter. Okay, what we do know is this, that matter is anything that has mass, okay? And we will learn that mass is, there's a difference between mass and weight. Though here on Earth, we use the two interchangeably, but we all know that, or if you don't, that, for example, if you weigh X amount of weight here on the Earth, if you go to the moon, you're going to weigh less because of gravitational forces. So weight is a function of the gravitational forces that you're in, but the mass is constant. Whatever mass I have here on the Earth, it will be the same amount of mass on the moon, okay? Well, what we know is this, that all matter, which has mass, is composed of atoms, okay? And these atoms, they themselves are composed of subatomic particles, which we will talk about, and that is the protons, electrons, and the neutrons. And we have learned since then that these guys are even made up of smaller subatomic particles, which is beyond the scope of Chem 130, but there is a final particle that has been found that supposedly is the final particle that consists of all the basic unit of the matter. It's amazing information coming out about that. But you look at it this way, you know, if I had a bunch of Legos, the same color, same shape, I'm sure some of you up there have worked with these Legos. Imagine, you know, the infinite number of things you can build with a Lego. Well, matter's the same way. These are all built with the same component, and we can build an infinite amount of combinations to create infinite number of compounds and molecules. It's just mind-boggling. All right, so as I mentioned, there are three states of matter, which again, you are well familiar with, okay? We got solid, liquid, and gas. Now you're gonna see throughout this semester diagrams as follows. We try to designate a solid and a liquid. Now, if you look at the solid section diagram here, you can see we got these little gray circles, little spheres. They're all the same shape, okay? But they're all nicely ordered and structured relative to each other, okay? And that designates, it's our means of showing you what a solid is. Very rigid, very ordered. Now, if we take the same material and we just loosen them up a little bit, and we get, again, we still have spheres here, but not as ordered. They're moving around. Okay, so that would depict a liquid. And then to the far right, they're totally separated from each other. I mean, it's quite a space between them, and that would represent a gas. Okay. Now, the interesting thing about all this is what we're looking at, these interactions that happen in between the molecules. Here in this case, a little arrow, you can see that where it drew. There's an interaction between two of the spheres, and we call those intermolecular forces. If they're real strong, that's what causes these molecules to hold on to each other very strongly, compared to the liquid, where they're not maybe held down as tight. There's attraction there, but they're not holding on very tight, so they're loose and they move around. And then in the gas phase, the interactions between molecules are very minimal, so much so that they just separate from each other. Okay, those forces are key, and all of those forces that keep these molecules either tightly packed or loosely packed are all attributed to the electrons that are floating around that molecule. Very crazy electrons. All right, so here we got solid, liquid, and gas, and these are diagrams depicting different states of matter. Now, what do we have here as some properties? Properties of solids. Again, you're well familiar with this. Solids have a fixed shape and a fixed volume. my cell phone. Here's a solid material. I got a shape of my cell phone. It has a volume that I can measure length, width, and height. Okay, that's volume, and it's all set. Okay. Um, the molecules will still vibrate relative in, all molecules move, even in the solid state. Within the molecules, they do move. In fact, we'll learn later on that at absolute zero, it is predicted that that's when all matter completely stops. But even in the solid phase, they're vibrating, and a lot of things going on in there with respect to the atoms. They tend to be, solids tend to be either a crystal or a non-crystalline material. Okay. And they're not very compressible. In other words, if we go back and look at the diagram depicting a solid, the round spheres are very close to each other, packed to each other. And like I mentioned earlier, what's around that circle, if you will, are electrons, and they're negative charge. And so think about this for a second. If I have a negative charge on one end, and then on the other side, I have another negative charge here, yeah, there's going to be a little bit of attraction, but there's going to be a lot of repulsion because negatives and negatives repel. And so these guys never really get, touch each other. And it's something to think about. Whenever you hold on to something, you're not really holding on to that item in your hand because you have electrons at the ends of your hand. And so it's electrons against electrons repelling each other. Okay. Not compressible. Now, most solids have a higher density. Now, what is density? We kind of introduced you to this concept a little bit early, but that's okay because we're going to use it quite a bit. Now, by definition, I give you the definition of density. It is a measure of mass. Its weight. Here on Earth, because we're on Earth and not someplace else, we kind of interchange the mass and weight. So we can go to the balance and weigh it out, and that is our mass, okay? Divided by the volume, and that is a ratio. We're going to use these type of ratios a lot. You're familiar with all kinds of other ratios, okay? We got mass over volume, miles per hour, that's a ratio, dollars per hour, another ratio. We're going to utilize these ratios and keep track of these units. Now, normally the units of density are grams per milliliter. Okay, so you can get a piece of solid, weigh it out, you got its mass in grams. Measure the volume out, now you got a volume, so you take the mass divided by the volume you measure, and you got a density, which is a physical property of a solid. Okay. A little side note there with respect to ice. If I were to take 1 gram of water and measure its volume, guess what? I will have a volume of 1 milliliter or 1 cc, another term for it. Okay, and so its density of water at, let me clarify here, at 25 degrees Celsius would have a density of 1 gram per milliliter, okay, of water. Now, if I take that same gram and I freeze it, what happens is that because of the property of water, that volume increases. What happens, the molecules get in an ordered state and very crystalline state, and its total volume increases. So now that same gram that I started off with might have a volume of, instead of 1 milliliter, we'll have a volume now maybe about 1.1. Now think about that mathematically. I'm taking 1 divided by 1.1. What do you think? I'm going to have a number greater than 1 or less than 1? Mathematically.
Last
1 divided by 1.1.
Less than?
It'd be less than 1. Exactly. Will be roughly a density of 0.9-ish grams per milliliter. Now, the water that was used to be liquid, now is ice, has a new density of 0.9 versus liquid water has a density of 1. And because a density of less than 1 than water, anything less than 1 will float on water. Anything greater than one will sink because it's a lot denser. For example, steel could have a density of about 19 grams per water. With 19 grams per water, it would just drop like a rock, okay, because of its density. Unless you take that same steel and flatten it out, make a boat, make a ship. That's a different story. So anyway, water has that unique ability to float. And that's why your ice cubes float, because it change its density into being less than one. And it's just the ratio of mass over volume that just changed. Okay. So density, we'll come back to that a lot. Now, solids, because they're rigid, do not mix with other solids. They don't diffuse out, they don't get out, they stay where they're at because they're locked in position. Unlike liquids, unlike gases, okay, they're not locked in. Now, with respect to liquids though, okay, liquids will take the shape of whatever container you put them in, okay? You've seen that before, sure. But they have a constant volume, right? If I take a gallon of milk, I have a gallon of milk, okay? But it has a particular shape based on the shape of that container. Now, if I take that same gallon of milk and I pour it into a big container, do I not still have a gallon of milk? Yes, I do. But what about its shape? Well, now it's got a new shape, okay? Because the new container is different from the milk container it started off with, okay? So liquids take the shape of whatever container they're in. Liquids flow at different rates. And that's because of those interactions of the molecules that have with each other. Those what we call intermolecular forces, IMF. We're going to have a full chapter on that property, IMF. And we'll be able to predict a lot of stuff, okay? By looking at the formula, we may predict whether this thing is viscous compared to something else. But again, that's related to these crazy electrons that are on the outside of the molecule and how strong these forces are with each other. Now, liquids are not compressible. Again, even though they are not as rigid as the liquids, they're right next to each other. So there's not a lot more room to compress. There's a little bit, but not a lot, which is a good thing because with this property, we wouldn't have, things like hydraulics. We wouldn't have power steering, power brakes, okay? Things of that sort, because we use hydraulics to help us deal with lifting heavy things. And using the liquid, in that case, it's an oil, a non-compressible oil. Liquids tend to have a higher density, so that ratio, mass over volume, they have higher density than gases, okay? Now, if the liquids are soluble with each other, they will mix. So, you can take soda, your soda pop, for example, is a mixture of liquids and some solids and some liquids, and they are soluble, so they mix. If they don't, they're not soluble, they do not mix, hence Italian dressing. Italian dressing, you got two layers, you got oil and water, right? Two totally different properties. The oil property and the water property, totally different. They don't mix at all. All right, now with respect to gases have no shape at all. Just like liquids, they take the shape of the container, okay? And because based on that diagram where we depicted the gases, there's a lot of space in between molecules. So gases can compress or expand, okay? Because as we increase the volume of the container, the atoms get further apart, okay? And if we decrease the volume of the container, the atoms get closer together. Now, at this point, gases do not have a set volume. There will be a point where we'll talk about it, where we talk about standard temperature and pressure, where gases do have a specific volume. But right now, at this point, Gases don't have a set volume. Okay, very low densities, and that's why they're out there in the air. Yeah. And the densities are very small, 0.001 grams per milliliter, for example. They tend to mix completely with other gases because there's really a lot of gap in between molecules. There's room for everybody. And our air is a mixture of gases: nitrogen, oxygen, carbon dioxide, a bunch of other gases, okay, throughout the air. So they mix. They exert pressure. That's because they're hitting the side of the container. Case in point, your tire in your vehicle or your motorcycle, whatever you're driving, you got a rubber tire, right? Let's say you got a vehicle, 32 PSI, pounds per square inch. Well, you go in, you walk in, you see the tire's a little low. PSI now is maybe 30 PSI or 25 PSI. All right, so pressure's down. So what do? You go to Quick Trips, wherever, put in some more matter, some gas matter. You add more molecules in there. There's now more molecules banging up against the wall inside the tire. Guess what? Pressure goes up. Okay. And they exert a pressure because they're pounding up against the container. Now, this particular table here will summarize these properties. For example, solids, yes, they have a fixed shape. And yes, they have a fixed volume. Okay. With respect to liquids, no, they don't. They don't have a fixed shape. They follow the shape of the container, whatever container it may be, but they do have a volume, a set volume. Okay. 1 gallon is still 1 gallon, whether I put it in a gallon container or I put it in a 55-gallon drum. Shape would be different though. Whereas gases do not have a fixed shape and do not have a fixed volume. Okay. We will talk about their fixed volume at a later date, but not right now. It's just no. All right. Physical and chemical properties. Now, we talked about the physical state, solid, liquid, and gases, and we designate them by these letters that are written right here. S, lowercase s, L, and G for solid, liquid, or gas. Okay. Now, when we talk about physical properties versus chemical properties, here's the thing. I'll come back to that in a second. Physical properties. These can be such things that they describe the chemical and some facts about the chemical. For example, the color. Maybe some chemicals are blue, yellow, pink, whatever, or colorless, or off-white, whatever the case may be. They may have a specific odor. For example, if you have gas at home to run your kitchen, they put in it a small amount of this sulfur-based compound that it's a small amount. And if you ever smell gas, it smells pretty bad. But in concentration, oh my God, in concentrated mode, that's some nasty stuff. So that's an odor for that chemical. Some of the things, for example, the mints that you may ingest, you put in taking a wintergreen mist, that is a chemical. Those are chemicals are called esters, and they smell pretty good. Banana oil, for example, is an ester. Banana oil smells very good. Okay. Taste, they may taste good. They may taste sour. These are physical properties. They may have a specific texture. The melting point, that is a temperature in which they begin to melt, self-explanatory. For example, a stick of butter. Take it out of the refrigerator, it's nice and solid, right? Put it on the pan, warm it up, starts to melt at a specific temperature. That is called the melting point. They also have a boiling point, and that is that temperature in which the liquid becomes a gas, okay? Its physical state, whether it's solid, liquid, or gas, its density is a physical property. Its solubility with respect to, is it soluble in water or more so soluble in oil? Is it more oil-like properties or more water-like properties? Things like, does it conduct electricity? And whether it's fairly hard. Metals obviously are pretty hard compared to, chalk, which is pretty soft. All right, so those are some of the things that define physical properties. When we look at the chemical properties of a chemical, a chemical could be explosive. TNT, dynamite, AKA dynamite. In my early graduate years, I worked with a class of compounds called peroxides. You're familiar with one type called hydrogen peroxide, but it's just one of a variety of different ones. There are some, like for example, on skin treatment, there's a benzoyl peroxide. That's an example of another peroxide, but those peroxides were very sensitive to pressure and temperature. We used to make them and store them in the freezer, and every time we took some out, we would have to alert the whole lab because everybody stopped what they're doing because that whole refrigerator could go up if we weren't careful. So is it explosive? Is it corrosive? Okay. Causes metal to oxidize and rust out. Is it toxic? Is it a poisonous? Hydrogen cyanide, extremely poisonous. Or it could be inert, which means it doesn't do anything. It just sits there. No matter what I do to it, it won't react. All right. Inert gold, for example, pure gold is fairly inert because the gold that was buried 20,000 years ago, and you unearth it, and it's still shiny as the day you went into the ground because it's so unreactive. Is it reactive? Is it rust? Does it oxidize? Or when you heat it up, does it break down and decompose? Those are the chemical properties. Now, with respect to physical properties, nothing happens to the formula. If I were to take, for example, we all know this, if I take an ice cube and I heat it, I make water, or liquid water, right? I got solid water and I got liquid water, but I've not done anything to the formula of water, okay? That is a physical change. That's important. Where am I at here? Hold on 1 second. Let me let them in. For example, we tend to write chemical reactions as follows. Let's say in generic form, I got A plus B, and that reacts to give me C. Okay, so this arrow represents that a process occurred, either a physical process or a chemical process. To the left of the arrow are my reactants. Those are the chemicals or whatever something's going to happen. And then to the right of the arrow, those are my products. And that's how we write chemical reactions. We write reactants, arrow, then products. Okay. Now notice I wrote the arrow in one direction. We will talk about some reactions that have a double arrow, meaning they go both directions. That's the equilibrium reaction. So some reactions can go back and forth at a certain rate. Okay. But that's how we write a chemical or a physical process. So how do we compare the difference between a chemical process and a physical process and the chemical process? Well, we're all familiar with H2O. That is water. Now, we take it and refreeze it. It's a solid, so its physical state we write in parentheses the letter S. Well, we heat that ice cube up, and we have an arrow to say there's a process going on here. And guess what? That water now becomes a liquid, right? We all know that. Okay. Now, chemically, structurally, we did nothing to the formula. H2O is still H2O as a product. That means it is a physical process. Okay. A physical process. Now, we can take H2O and do something else. We can take H2O, water, okay, and if we hit it with some electricity, some energy, guess what? We're going to break it up. We're going to break up the molecules back to the elemental form. And we're going to create hydrogen gas plus oxygen gas. And I write it 2 here for a reason. I'll explain that here in a bit. And so in this case, water was decomposed and broken back to the elements. So that is a chemical reaction. Okay. So if we can find water out in space, it's very important because we can make fuel, H2, and guess what? We can make O2, which we need to breathe with, right? All right. So that's the difference here between a chemical process and a physical process versus a chemical process. And also this page lists the difference between physical properties and a chemical properties. All right. So these changes of state, I'm not telling you something you all don't already know, okay? When a solid goes to a liquid, guess what we call that? Melting. That stick of butter, right? It's solid, we heated it up, it melted. All right, so there's no rocket science here, right? Okay, now if we take a liquid and we keep heating it, guess what? It becomes a gas. Again, if we got solid ice cube, we heat it, becomes a liquid, we continue to heat it, guess what? Now you got water vapor, you got a gas, right? What do we call that? We call that boiling. We call that vaporizing and also evaporating, okay? When you take a gas and you converted it back to a liquid, what do you think we call that? Condensation. For example, I got a nice cold soda pop I got here. And the outside, I got liquid. Any idea where this liquid on the outside of my glass came from? We call that condensation, but where did that liquid come from? Magic? Got some Harry Potter stuff going on? Where did that liquid from outside my container come out? And you see now you've got yourself a nice ice cold drink with ice, and you let it sit there for a while, and then the whole outside is nice and wet. Or you go to Circle K and you pick up one of those pops, fill up with ice, and the outside gets all condensed. Where is that water coming from? Any ideas?
Is it coming from the molecules in the air?
You got it. Because they're all around us. Now, it's not so much in Arizona because it's somewhat of a dry area. We do have humidity. But when I look back at the humidity back in the 50s and 60s, it's changed quite a bit. It's a lot more humid than it used to be back then. Our ecosystems changed here quite a bit. So anyway, we've got water molecules in the vapor phase, in the gas phase, all around us. And so when they come around and they hit my glass, which is cold, these water molecules are high on energy. It's a matter of energy, transfer energy. Always goes from high to low. So we got high energy out here in the atmosphere. They hit my glass, they transfer that energy, they lose that energy to my container. That's why my container will eventually get warm. Okay. That molecule will come down, and then what happens when it loses the vapor phase loses that energy, and then the other molecules get attracted to each other. They go from the gas phase to the solid phase, and they condense. And that's why the outside container gets wet. All right, that's called condensation. Now, there might be some others that you may not be familiar with. Okay, when we get a liquid going to a solid, what do you think we call that? Or not this one. And this one you should be familiar with. Liquid to solid. Those of you freezing. Exactly. Very good. Exactly. So it is. Now these two you may or may not be familiar with. There's some liquid, some matter that will go from a solid directly to a gas. It's like, yeah, it passes the liquid, but it passes so fast, for all intents and purposes, it's not even there. Okay. And we call that sublimation. Now, can I give you an example of this? Sure. Go to Fry's buy some dry ice. Because dry ice is nothing more than carbon dioxide, which is a gas normally, that has been put under a lot of pressure and condensed and made into a solid. And so when I take that carbon dioxide and I put it out here by itself, guess what? You get all that carbon dioxide that's in the solid form goes right into the gas form, dissipates very quickly. So also your plants, if you got plants at home, they will like that carbon dioxide, that dry ice. Why do you think? Because plants need carbon dioxide. So put some dry ice around your plants, they'll be happy. And then they'll reward you because then they'll fill up your room with oxygen, which is what we need, right? All right. And if you don't have carbon dioxide, you can talk to your plants. Why would I talk to my plants? I'm going crazy, right? No. Why would I talk to my plants? Yeah, it'll help my well-being, but what are the physical process? Remember that hamburger in the beginning slide? When we exhale, what do we exhale? Carbon dioxide. All right. So your plants will like that. All right. So if we take that same gas, carbon dioxide, and then revert it back to a solid, we call that deposition. Okay, that's how we make, for example, dry ice. Some other examples, I said dry ice, but some of you may be familiar with, oh my goodness, mothballs. They call it a mothball little disc, you know. It's naphthalene, but it's a solid that goes into the gas phase. All right, so physical changes, as I explained earlier. Here we have an example of water, H2O, that's in the liquid phase that is going into the gas phase. Okay, so we have a physical process here. Why do we have a physical process? Because again, H2O is still H2O when it's done. Okay. Nothing was, the chemical formula was not changed at all. Well, we're going to learn about this when we say H2O. What this tells us is that there are two atoms of hydrogen and one atom of oxygen. And we're going to learn later on about how to put them together to write a structure. And we're going to be able to show you that this is the structure, and these two little dots represent what we call lone pair electrons, but that's coming down the road. Okay. All right. So there's a physical change. This diagram depicts all of the physical changes we talked about. Solids going to that are melting go to liquid, and liquids going to boiling to go to gas. Now, all this, these are physical changes. All this is about the interactions of the molecules with each other. Okay, and so for as I stated here. Let me draw an arrow, but better. If we look at in between the spheres, those interactions are what keeping those molecules attracted to each other, those intramolecular forces. And when we put energy into the system, like I put plus energy by heating it, guess what? We break up that interaction. And now they become less organized, okay, and become a liquid. And if we continue to put energy into the system, plus E, energy, we finally break up that interaction very hard, and they separate the molecules from each other. And so now the interactions between the molecules they're further apart, they're not so strong. We can reverse the process by removing energy. So I put minus E. I'm taking energy out. I'm cooling things down. And I can take the gas, bring it back to liquid, continue to remove energy from that system, and bring it back to a solid. Okay? And it's all about the loss and the gain of energy depending which direction we're going for physical state. We know, for example, that if I have a cup of water and a cup of honey, and I do the race where I empty the cups, who do you think is going to win? The water, exactly, right? Well, how can I make the honey flow a little faster? What could I do? Any idea?
Yeah. Heat it up.
Exactly. I heat it up and I break up that interaction, make it more of a liquid. And that's what I'm doing. I've not done anything to break up the structure. All I'm doing is breaking up the intermolecular forces between the molecules. Okay. Which is driven by these crazy electrons again. All right. So as I stated, atoms are always moving. Well, let me ask you a question though. Why, if I were to take a container of water, H2O, and I set it on my kitchen table for a week or two, wouldn't that water all evaporate at the end of that time period? Yeah, that container would be empty. But why? When it started from here to here, why is that container empty?
Slowly
What
getting energy from the sun.
Well, let's put it in, I'll tell you what, let's put it in your kitchen. Okay, and away from the sun. Or put it in a cabinet. Close the cabinet up. Maybe it might take them about 2 weeks, but leave it there.
Does it just react with the air somehow?
No,
No?
thought process, that's okay. See the brain's working here, that's good.
Is it still
Right.
getting energy from the ambient temperature?
Okay, well, at the ambient will be, in order for water to boil, when you're gonna put a pot of water to cook some spaghetti, you turn it on, that temperature has to go to 100 degrees. The boiling point of water is 100 degrees, okay? So if I have a glass here and it's an ambient temperature, I'm at 25 degrees Celsius. So it's not gonna pick up a lot of energy enough to get it to boil, okay? Unless something magical happened in your cabinet. And if it got hot spontaneously, or let me know, we'll publish a paper, because energy came someplace. So here we are, 25 degrees, not 100. If I wanted to boil this and, make a pot of water for spaghetti, I got to boil that thing up to 100 degrees, okay? Well, let me tell you here. Atoms are always moving. And so if I were to take a look at this beaker and I had a, super duper telescope, I can look inside, okay? And then magnify that, here's my liquid. Magnify that and I will find, the spheres here that represent the water molecules. Well, these guys are moving around. They're just spontaneous. They got energy, even at 25 degrees, they're moving. And like shooting pool, one of these can collide into another one. And if it's on the surface, it can transfer that energy it collided with the one that's on the surface. And guess what? That guy that's on the surface gets kicked out. He's in the atmosphere. And then that process continues because these molecules are not stationary. They're moving around. Okay. And that explains why at 25 degrees, you got water that will evaporate. Even if you have a fingernail polish, you fill that up with fingernail polish, which is acetone, I guarantee you and don't heat it and just let it sit there. Within a few hours, it will evaporate. It's because, again, the molecules are banging up against each other and and they're not being held closely together very well. So eventually they're all of them are going to kick out. So it's just the internal energy of the water molecules and the transfer of one molecule, its energy onto the other. It is about the transfer of energy. Okay. Hey, think about it. Cold winter day. You take a nice hot shower, right? Early in the morning. Everything's nice and warm in the shower. All right, you're done with the shower. You step out. Does it get cold? Did you step out? Yeah. Okay. All right. So it gets real cold. When you step back in, does it warm up again? Yeah, you warm up a minute. You step into the stall. Okay. Now what's happening there? All right. Remember, energy goes from high to low, always. It doesn't spontaneously go up. Energy goes downhill. Okay. It doesn't spontaneously go uphill unless you put energy into the system. And so you're in the shower. Your temperature now is warm. You're at a higher temperature than outside the shower. So as you step out, you are higher in temperature than the environment. So hence the temperature goes away from you to the environment and you get cold because your energy level drops. All right. So now, when as I step back into the shower, I warm up again. Why? Because now you are at a lower energy state than the shower is. And so that energy from the shower goes to you and you warm up again. Okay. And you feel a little bit better. So it's a transfer of energy. All right. So when we heat up ice, these molecules are gaining what energy? We call it kinetic energy because it's moving energy. Okay. And if they absorb enough energy, you're going to cause that ice to separate the molecules, separate from each other a little bit better, to go into the liquid phase. And if you continue to give it energy, it will eventually go into the gas phase. Okay. It's all about energy. Now, to take the gas, you can revert that. Wow. How? By taking energy out of the system. So you could take a gas, and bring it into a solid phase or even a liquid phase. Liquid oxygen, for example, you take oxygen gas and you put it under extreme pressure enough so that the molecules start to attract to each other for what they can, being gases, and then they go into the liquid, but only under high pressure. If you got a lighter, butane lighter, flick your Bic. Butane, which is a hydrocarbon, is a gas at 25 degrees. Okay, but put under pressure, you've made a liquid, so now you got your little butane lighter. Okay. All right, chemical changes. Chemical changes are processes that the formula changes, the formula of the molecule. Okay, because the molecules are broken apart and rearranged. You're breaking up bonds and you're making whole new bonds. You're making whole new compounds. Okay. These are also known as chemical reactions. Okay. The starting material, whatever it was, is destroyed and you have created new material. So if, carbon is in the form of a hydrocarbon and you burn it, now it becomes carbon dioxide. It's still carbon, but it's in a different form. Okay, just like that very first slide example I gave you, I showed you about the grass and the hamburger and so forth. For example, we have an example here called burning gasoline. This is an example of one of the 6 types of chemical reactions that we'll eventually talk about. This is combustion. You're familiar with this, okay? Now, what you may not be familiar with is the designation we have down here. We have CX, and HX. X represents a number, and it could be variable. We call these hydrocarbons because they are made up of nothing but hydrogen and carbon, okay? And the smallest hydrocarbon there is CH4, and that's called methane. Yeah, butane's got 4 carbons, and so on. We won't go into detail, but that's just a general formula for a hydrocarbon. To burn anything, to combust anything, actually, you require oxygen. Without oxygen, nothing's going to burn. Okay. Now, for Chem 130, when you take a hydrocarbon and you have in the presence of oxygen, the only 2 products you're going to make is CO2, aka carbon dioxide, and water. Yes, I know that when you combust gas, that you can get carbon monoxide plus a series of other things. And the reason you get carbon monoxide in our vehicles is because our engines and carburetor systems are not very efficient. Yeah, and so they don't. The hydrocarbon doesn't burn efficiently, and we end up making carbon monoxide. Notice that introduction to the beginnings of naming. Okay, carbon monoxide, carbon dioxide, 2 oxygens versus 1 oxygen. Poisonous gas, carbon monoxide. Well, not poisonous to us, but very good for the plant, carbon dioxide. And water. So if you ever, you're driving along the way and you look at the tailpipe, occasionally you might find one that's dripping the liquid. Well, guess what? That liquid is water vapor coming out. All right. All right. So, and that is a chemical change because we have totally changed the structure of the hydrocarbon, and now we made it into a new molecule. It's still carbon, okay, but it's totally different type of molecule now, compound. And that is a chemical reaction. We totally change the reactants to make whole new products. Now, what indicates a chemical reaction? These are general observations that they not always true, but it's 90+% it is. Well, oxidation of matter, for example, something that burning is a chemical reaction. Whether you're burning fuel in your car, or whether you're burning wood in your fireplace, or whether your pickup truck is an old one and it's got rust, okay, like that. My old truck used to have. That was a chemical reaction that occurs, okay? Occasionally what can happen, you might see bubbling without any heat being given off. No heat, not high, doesn't get hot, but there's bubbling. A good example would be the Alka-Seltzer tablets, okay? Which to this day, I don't know why Alka-Seltzer, why they make it bubble, because what they do is if you look at the labels, they put citric acid, and then they put a bicarb solution, solid in there. Now, it's an acid in the base. The sodium bicarb or baking soda, when that reacts with the acid, it creates carbon dioxide, it bubbles. Okay, so I don't know why Alka-Seltzer would, they want it to bubble. The only thing I can think of is it maybe helps it mix the stuff up because the active ingredient is the acetaminophen or whatever else is in there. Anyway, Alka-Seltzer is a good example of a reaction occurring by the bubbling. Sometimes you get 2 liquids that are clear, okay, and you put them together and they precipitate. It's solid forms, okay, precipitation. That's how we test for a lot of things that we're testing for, let's say, chlorides in your water. We hit it with silver nitrate. Silver and the chloride get together and it forms a solid because it's not very soluble in water. And that's a positive indication for, for chlorides. Release of heat. For example, you go to CVC pharmacy or Walgreens, wherever, and you can buy a hot pack or a cold pack. You buy a hot pack, you get it to smash the bag that mixes the chemicals inside, and it gets hot. You use that hot pack, you're out there running, whatever, you strain a muscle, and they tell you put a hot pack on it. All right, so you can buy that. They also have a cold pack. Again, similar scenario. You smash up the chemicals in the pack, and it gets cold. The hot pack is exothermic. The cold pack is endothermic. or light is emitted. Glow sticks, classic example. The glow sticks, you got to break that little container inside. There's two chemicals. One's inside a little glass container. You got to break it, and then they mix up, and then light is given off. Okay, so those are good indicators. In fact, fire bugs, lightning bugs, there's a chemical reaction occurring in their tails. Change of color or an odor. I talked to you earlier. I mentioned about wintergreen. Smells pretty good, using breath mints and so forth. But they're made up of an alcohol and an acid. Separately, they don't smell too good. But you put them together and you get a nice, sweet smelling smell from these chemicals. So, or they may change color. So those are some indicators that a chemical reaction occurred. Okay. Now, let me give an example of a chemical change. And let me explain to you how drastic change that occurs by simply the transfer of an electron. We're going to learn about the electrons and tell you how small they are. Analogous, if I were to weigh an electron, let's say I'm a proton and a neutron, one electron would be about maybe 1 or 2 hairs in my head. Tiny, tiny guys, but yet they have such a drastic effect on a lot of stuff. All right, let's take this example here. What we have here is a chemical reaction. Now, on the far left, we have sodium metal. Here's the formula, Na. We're going to eventually, we're going to be responsible to learn at least the first 20 symbols and formulas. Sodium is number 11. Its symbols Na, comes from the word natrium, Latin term. So that's sodium, okay? Then we have Cl, which is element number 17, which is chlorine, okay? And notice here there's a 2, okay? A 2 means, subscript 2 is diatomic. What that means is this. There's 118 elements on the periodic table behind me on my screen here. Of those 118 elements, only 7 of them are what are called diatomic here on Earth. Means that by themselves, they cannot, they're unstable. So they have to hook up with another one of itself to be stable. Chlorine is one. Oxygen's another one. We're going to learn about hydrogen gas is another one. They're diatomic. Okay, but more on that later on. The point is this: sodium metal is extremely reactive. You can Google this. You can see some crazy guys, people, taking some sodium metal and dumping it into some river, and the results are quite drastic. Sodium metal is extremely reactive. It reacts very violently with water. It gives off a lot of heat, and it gives off hydrogen gas, which, because of the heat, ignites a hydrogen gas and gives you a nice little explosion. Okay, very dramatic, very hazardous. So you wouldn't put that in your mouth by all means, okay? Now, chlorine, Cl2, is a poisonous gas. Now, we all smell chlorine if you're around, like Clorox, you might smell that it has a little bit of chlorine smell in there, or you're on swimming pools. A lot of municipalities or water treatment plants use chlorine gas to treat the water to get rid of bacteria. So be careful if you live around one and you ever happen to see I'm having a senior moment, a yellow cloud of gas, that's chlorine gas, get upstream immediately. Very poisonous. It will just rip up your lungs bad. So we got a hazardous metal. We got a poisonous gas. They react together, and I can put that stuff I circled in my French fries. Okay. Sodium chloride. Okay. AKA salt. Now, let me introduce you to something. We are used to, if you're not, non-chemists are, when we think of salt, we think of sodium chloride. But in chemistry, salts, there's a lot more salts than just sodium chloride. With this could have been potassium chloride, magnesium chloride, anything. Salts are a combination of a metal and a non-metal, but we'll get back to that. The point of all this is there's a transfer of 2 electrons from sodium to chlorine. 2 electrons. And that simple transfer creates sodium chloride, aka table salt, which is not hazardous unless you got high blood pressure, and then you want to maintain your sodium intake wants to be lower than normal. Okay, so those electrons are pretty intense. But this is an example of a chemical reaction. We have completely converted reactants into making totally different products. Can we take sodium chloride and go backwards? Yeah, but it takes energy to put it in to create, just like I can take water and make hydrogen and oxygen, okay? But it takes a little bit of energy to put it in. Now, if I take hydrogen and oxygen and I put them together, that's spontaneous. That reaction proceeds pretty quick. Not a rockets use that fuel, oxygen fuel, hydrogen fuel. All right, so that's an example of a chemical change right here, okay? So now we have a series of 5 reactions. Now, I know you're not familiar with the formulas. That's okay. What we're asking you to do here is to analyze the reactants and the products, okay? Let's take the first one. We have something that says is nitrogen and 3 hydrogens. So NH3, and guess what? This is the reactant. Then we look over to the product side, and guess what? It's the same formula, NH3. What does that infer? Okay, physical change, right? Physical change. I'll tell you what that NH3 is. You're probably familiar with it. If you have dirty diapers running around, you got kids, ammonia, or you use it to clean your windows, ammonia. That is the formula for ammonia. Okay. But NH3 in the beginning, NH3 at the end, you can see that the physical state, it went from a gas to a liquid. So it's a physical change, okay? Now, a little bit different now. Now, for right now, disregard the numbers that we put up front, but I'll introduce you to these right now, okay? These numbers we're gonna learn later on what they mean. For right now, it says I need 2 molecules of NH3. Something happens to them, and guess what? I make nitrogen and I make hydrogen. This plus sign tells me that I make 2 different products. Okay. So ammonia was taken and it was decomposed and broken up to make NH2, which is nitrogen, is one of the diatomic elements, and to make H2, which is hydrogen, one of the other diatomic hydrogens. Like I said earlier, there are 7 diatomic atoms. I already introduced you to oxygen and chlorine, and then we got nitrogen, and now we got hydrogen, and now we got 4. So we just got 3 more we got to be familiar with and be good to go. Of the 118, there's only 7. All right. So you can see here that this example, number 2, is an example of a chemical change. Okay. All right, the next one. Again, you might think, well, H2O, whoa, you might think water, right? That's a good, reasonable conclusion. However, guess what? There's a subscript in oxygen, in the O. So there are 2 hydrogens and 2 oxygens. We don't know what that is, but I'll tell you what it is in a bit. So we got this H2O2, and again, guess what? We got a plus symbol here, so that is a flag for me to tell me I got a chemical process here because I created 2 new products. Okay. And yes, indeed, number 3 is an example of a chemical reaction. Okay. What that H2O2 is, well, I'll let you know. I'm sure you used it. If you ever cut your finger, You put a solution of that on your cut finger. If you ever color your hair, you may have used some of that. Any idea what that might be?
Hydrogen peroxide.
You got it. That is the formula for hydrogen peroxide. Okay, FYI. All right. And now we look at number 4, and we still maintain H2O2. And guess what? It's still H2O2. Okay. So again, physical change, right? Because we still maintain the integrity of the structure before and after. And all we've done is just change its physical state. It went from a liquid to a solid. So it underwent freezing. Right. So that is a physical change. And then finally, the last one, we have C6H6, which if you recall from the general formula of CXHX, that's just simply a hydrocarbon. I'll tell you what this is, what this represents here in a bit. But again, we look at the reactant, we look at the product, remains the same. This hydrocarbon remains C6H6 before and after. The only difference is the physical change. It went from a liquid to a gas, so it looks like it underwent boiling, okay? Which is a physical change based on the reaction. Now, if we were to combust this, then it would be CH. If we were to combust that hydrocarbon, then it would be C6H6 plus oxygen. Okay, to give me carbon dioxide plus water. That would be a chemical reaction because we have busted up that C6H6 into carbon dioxide and water. That, ladies and gentlemen, C6H6 is called benzene. It's an organic compound. Causes cancer. A lot of transformers used to have it up there. If you got transformers around you, they ever bring them down, like EPS or whomever brings them down, keep the kids away because there's an oil inside these transformers. And the ones, these old fashioned cylinder shaped transformers. Anyway, there's still some around. What do we got? Oh, 2 more minutes. All right. Let me see if I can get you up to the 1 o'clock. Give me 2 minutes. All right. So elements. Elements, by definition, we're going to talk about elements, compounds, and mixtures. Okay. An element, there's 118 elements. It is one type of atom only. Okay. So we got He, which is helium. Okay. We're going to ask you to learn you must start learning the first 20, the symbol and the name. And we'll get to that. There are some, specifically 7 of them, that are diatomic elements. We call those molecules. And they're diatomic. For example, oxygen. Okay. But the point is this: if you take that atom, you can't break it down any further to another element, I should say. If I take that element, if I do anything to it to break down further, now I broke it down to the subatomic particles. It's no longer that element to a certain extent, depending on what I do to it. Okay, but that's what an element is. I can't break it down any further. Now, with respect to a compound, how do we define a compound? That is a combination of 2 or more different atoms. For example, we did the sodium chloride example. Okay, sodium chloride. Sodium and chloride, that's a combination of 2 different atoms. Hence, this is a compound. Chlorine is simply 2 chlorines. Okay, that is an element. Okay, it's not a combination of 2 or more different elements. Chlorine is diatomic. You know, structurally, we will put a line between the 2. That's what chlorine is. Our structure is for chlorine. Okay, so that's an element still. The elements are still the same. Okay.
Fred, can you hear me?
Yeah, go ahead.
So for the question on our study guide, It say
Uh-huh.
identify diatomic elements.
Uh-huh.
The elements.
It broke up. I heard okay, identify the diatomic element.
Yes. So
Okay.
would that just be the description of element?
Yes, a diatomic element is, we call it a molecule just to represent, it's a molecule. It's just two elements together that are the same. And there's only
Okay.
there's only 7 of them. Okay.
Okay, so we should figure out what 7 of them are and
Yeah.
identify those.
In fact, we have a little thing here for you, and I'm just going to do it real quick. And we just call it a day here in a second.
Okay.
Remember these words. Have no fear of ice cold beverage or beer, whichever you're liking. Have no fear of ice cold beverage. Okay. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and a bromine. Okay. Have no fear of ice cold beverage. And those are the 7 elements that are diatomic. Those are the only ones. That means that at here on Earth at room temperature 25 degrees, they exist as diatomic because singly they are not stable. Okay. Now it doesn't mean that on some other planet with different conditions, higher temperature, different things, maybe in surface on the moon, they exist as single atoms, but here they don't. They exist as diatomic. Okay. And then, so 7 of them and 118. So there's 111 elements that are not diatomic. And we'll learn more about these properties of the elements. Of the 118 elements, only 2 are liquids at room temperature. Okay. Everything else is either going to be a gas or a solid. And the majority of them are I think there's 12 gases, 2 liquids, and the rest of them are all solids. Okay.
What are the 2 liquids?
Any idea? By chance? One's a metal and one's a metal that used to be used.
Mercury?
Mercury. Okay. And then there's one more, which is not non-metal. Bromine, bromine. Yeah, bromine. And then we had like 12 gases. And then, like I said, the rest of them are solids, which is good to know because, you might be given a reaction and then you ask to write the reaction, then you need to know the physical state of those elements. And by knowing which ones are, only 12 gases, 2 liquids, then by default, everything else is solid, right? Okay. All right. Well, let me stop it here. And let me clear this up. Ruby Rose. Come here. Somebody's trying to get my attention.